Hi, I'm Ron and welcome to PopScicle, where I talk about popular culture, science, and everything in between. In episode 7 of PopScicle, we talked about the types of stars out there and how these types can lead to the formation of life on the planets that revolve around them. Now, as a continuation of our world building topic, we'll be going into how life itself can originate on these planets that are supported by the energy of stars. Of course, what we know about origins of life is based on what we know of how life began or possibly began on Earth. Because as far as we know, Earth is the only planet in the universe with life. Of course, being a big science fiction fan, I am not willing to believe that the universe is as boring as Earth being the only planet with life on it. Now, with regard to the complexity of life, we don't know. It's quite possible that the Earth is one of very few planets that have intelligent life, but that there's life of some form out there is very likely. So the question becomes, how does life originate on a planet? Given that we have energy from the star, we've already established that that's very important. In fact, according to the Drake equation, that's the most important. That's the first step toward evolution of life on any planet. The question now is how life can take a foothold on a formerly lifeless planet. And so we turn to the Earth's own history. Based on evidences that we can find, we can say that life on Earth is probably anywhere from 3.5 to 4 billion years old. Now, if you read science texts from, let's say, 10 years ago, you'd see a figure closer to 3.5 or to 3.8. And these are based on fossils that have been found of microorganisms or what look like microorganisms. And so it's believed that the prototypical life forms or the first ever life forms, the last universal common ancestor of all life on Earth, evolved at around this time. But there have been recent evidences, for example, carbon-14 isotope records in 4 billion year old rock deposits have been found. And this particular isotope of carbon is often associated with life. And so it could be as old as that, which would be quite surprising because as far as we know, oceans on Earth did not become very stable until around 3.9 billion years ago, because until then, the Earth was still being pummeled repeatedly by ocean vaporizing impacts of asteroids and all sorts of heavenly bodies. Regardless of the date, there are three prevailing hypotheses on how life began on Earth. Now, these are not necessarily mutually exclusive. You can have a combination of these things, but let's tackle them very quickly, one by one. Let's start with the one that's most sci-fi in flavor, and that's what we call Panspermia. The term Panspermia literally means seeds everywhere. Spermia referring to seeds, pan referring to everywhere, or a widespread distribution. So, what is panspermia? It's essentially the idea that life on Earth, or the ingredients for life on Earth, namely the building blocks of life, the organic compounds, carbohydrates, amino acids and proteins, lipids and nucleic acids, came not from within the Earth, but from outside it. So it's an extraplanetary or extraterrestrial origin of life, or the building blocks for life. So what does that imply? If this is really how life came to be on Earth, then all life on Earth owes its existence to an extraterrestrial origin, meaning we are products of either spores, microorganisms, very primitive organisms, or again, the building blocks from outside the Earth. If you're thinking that this is too far-fetched and too much going into the realm of science fiction already, you'd probably be surprised to find out that there are organic compounds outside the planet, on heavenly bodies, on asteroids, on comets. There are certain organic compounds, and these organic compounds are likely to be found on moons and planets also. So it is not really unlikely that you would have these ingredients raining down on Earth and eventually seeding the Earth either with life directly or the building blocks for the life. Now, of course, the more sci-fi aspect of panspermia is what we call directed panspermia, which is where an intelligent civilization outside of our planet intended or intentionally seeded our planet, among others, with the ingredients for life. or the most primitive life forms to begin with. Now, I'm pretty sure that you know some science fiction texts that support the panspermia hypothesis. A very recent one is the Prometheus movies that are within the Alien franchise. And it's very clear in a particular scene in the movie where the engineer deposits part of his biological material into the planet. That's an example of directed panspermia. In science fiction literature, the two most important examples are The Known Space Universe by Larry Niven, which includes Ringworld, and The Heinisch Cycle by Ursula Le Guin, which includes The Dispossessed, The Left Hand of Darkness, and several other works by that author. So these are both popular works of science fiction literature that suggest that a hyper-advanced and intelligent race intentionally seeded different planets with the ingredients for life. There's a particular episode of Star Trek The Next Generation called The Chase, which touches on panspermia very elegantly and in traditional Star Trek style, which is all about exploring the unknown and shaking the foundations of knowledge. And this is a very, very interesting episode because it also touches on some questions about evolution, but also, the sentiment of shared origins, which is a beautiful message to talk about, particularly during these times when we are faced with so much uncertainty and so much division among us because of different ideals. So when you have a science fiction show like Star Trek The Next Generation, reminding us that, or telling us that even if we're talking about multiple alien species and humans, we share origins, and so we are more alike than we are different. And that's a beautiful message, right? There's a beautiful short film called Biogenesis, which is available on YouTube, and I've provided the link below. So I suggest that you watch it. It's only around 4 minutes long. And it touches on panspermia, but also on one of the other two hypotheses on the origins of life. And so it combines these two into a neat, very artistic package. And so we go to the second hypothesis now, which is the primordial soup hypothesis. If you've taken any biology class in the past, then you've probably heard of the primordial soup hypothesis, often also called the Oparin-Haldane hypothesis, named after the two scientists who really elucidated a lot of the principles behind it. Now, it's actually pretty sci-fi in flavor also, if you think about it. In fact, one of the major arguments against it is that it seems to be very unlikely. And in fact, that's true. The chances of something like this happening on any planet are very, very, very small. However, of course, that is not to say that it's impossible. And that is one very important thing to remember when talking about such things as origins of life or evolution. Even if the chances of something happening are pretty small, that doesn't mean that they cannot happen. Now, going back to the hypothesis, the basic idea here is that life originated through abiogenesis. And that's what I was referring to. The short film Abiogenesis touches not only on panspermia as an idea on the origins of life on a planet, but also on the primordial soup hypothesis. So what is abiogenesis? It's essentially formation of life from non-living things. We know now that life can appear or can be produced only by pre-existing life. That's a key basic principle to life, universally, as far as we can tell. For there to be a living thing consisting of cells, it has to come from pre-existing cells. So it's part of what we call the cell theory. So you cannot have spontaneous generation of life from non-life. However, if you think about it, life had to come from somewhere, right? And that something, that somewhere, had to be a form of non-life first. And so at the very beginning, there was abiogenesis. And specifically, this is a type of abiogenesis that is chemical in nature. Now, it's very important to set the stage for the primordial soup hypothesis. This is the same, you can assume that this is the same stage that was also existing before life evolved on Earth for any of the three hypotheses. Life at its beginning until around 3.9 billion years ago was a hellish place. It was constantly shaken by eruptions from the newly forming core and crust because it was a new planet that was still being bombarded by heavenly bodies. There were constant volcanic eruptions and constant lightning storms because of the active charges in the quote-unquote atmosphere. I put it in quotation marks because it wasn't even a distinct atmosphere or a blanket of a distinct layer of gases. Yes, there were gases in that early atmosphere, but they are very much unlike what we have now. Whereas much of our atmosphere consists of nitrogen and oxygen, at that time there wasn't any oxygen. Instead, there were gases like methane, ammonia. Of course, there was already carbon dioxide and nitrogen. There was water vapor. But think about those first two that I mentioned, ammonia and methane. Think about inhaling that atmosphere. It's like inhaling the gases in Venus. Now, we have to briefly say that there are already debates as to whether there was actually a lot of methane in pre-life Earth's atmosphere, because there are evidences supporting that idea, but there are also evidences supporting the idea that there was not a lot of methane. There's also some controversy as to whether the Earth was very hot or very cold at that time. However, that is not to say that there are too many inconsistencies with regard to the primordial soup hypothesis. So essentially, the volcanic eruptions were providing a lot of thermal or heat energy, whereas the lightning charges were providing a lot of electrical energy. And what's important to note is the gases. Again, methane, questionable, we're not sure about it, but ammonia, carbon dioxide, these were probably present in that atmosphere. And so what happened was that these electrical charges and the heat from the volcanic eruptions charged these gases, and what came as a result were the basic building blocks of life. Amino acids, which would form proteins, simple sugars, which would form carbohydrates, nitrogenous bases, which would form nucleic acids like DNA. These were eventually formed from that interaction between the heat and electricity and the gases. Does it sound far-fetched? Well, there has been a lot of evidence supporting it. In the 1950s, there was a classic experiment by Harold Urey and Stanley Miller where they set up this very simple, elegant series of tubes where they started off with just water, a source of heat that would turn the water into water vapor and thus circulate it in the tubes and vessels. And there's that chamber with electricity being created to simulate the lightning charges of pre-life Earth. And in that flask or that chamber with the electrical charges, there are also the gases that are thought to have been there in pre-life Earth's atmosphere, namely methane, ammonia, and the others. That was everything that was in that series of tubes and flasks at the start, but then after a while, you had at the collection vessel at the end amino acids and simple sugars. So this was a very simple, elegant proof that what is speculated to have happened by the primordial soup hypothesis really did happen. And then, of course, it was a matter of these building blocks coming together to form polymers and then eventually forming spherical bodies that would eventually become the first cells. But it was an abiogenic origin. Now, this is the one that's supported the most by evidence, but there's a third hypothesis that's enjoying a lot of support nowadays, and that's what we call the iron-sulfur world hypothesis, which posits that instead of life evolving or originating above the surface of the water, it probably originated under it, particularly where you have hydrothermal vents. These are fissures, cracks, mini volcanoes that spurt out very high temperature water vapor or gases. Because where water comes into contact with magma through these fissures, then of course, that creates water vapor, that creates a gaseous form of water, and it contains a lot of minerals like iron sulfides and other inorganic minerals that are very rich, currently being used by a lot of living organisms in the deep sea, but also potentially, possibly, these may have been used as substrates or ingredients for the early forms of metabolism by primordial life forms. And so we can say if this is really the hypothesis that explains the origins of life on Earth, life began in the deep sea and from inorganic minerals like sulfides, iron sulfides, and the like. So it's a very interesting idea, and like I said, there's a lot of support going on there. This is probably more fitting for worlds in science fiction where life is speculated to have originated under the water, and there's a lot of mystery to the ocean, particularly to the deep sea. So there's a lot that you can play around with when writing sci-fi stories in terms of origins of life. Now, there aren't too many science fiction texts that really dwell on the origins of life on a particular planet. Not a lot of science fiction texts would go that deep into world building. And so it's not really necessary, just like with episode 7 where I said it's not really absolutely necessary for you to explain what kind of a star your planet has and how that led to the evolution of the particular life you have in your world. However, as with that, knowing these possible ways by which life originated on Earth and possibly on other planets may enhance your writing and may inform your writing also. And it's up to you how deep and how far back your world building goes. You might want to dwell on how life began on your worlds, because ultimately that would also serve to explain what types of life forms can evolve on your planet. So that's just a short overview of something that I teach for quite some time in my biology classes, particularly when I talk about the origins of animal life on Earth. I hope you learned a bit from it, and I hope that you can use this in your science fiction texts. Now, if you liked what you just saw and you would like to see more on science and popular culture and everything in between, don't forget to subscribe to PopScicle so that you may be alerted to new content. See you again soon!